the world's first electronic computer.
In 1 second, the computer can perform more than 1 million arithmetical operations.
Advanced microprocessors like the 286 or the 386.
Potential Y2K computer crashes top the list.
And we are calling it iPhone.
It's part of a popular movement in the technology industry. It's called cloud computing.
And you'll see why 1984 won't be like 1984.
Hello, and welcome to Magnetic, the history of computing. This is episode 3. The electrical age is here. In the early 1800s, if you wanted to do any kind of analytical work, or work that required a lot of math, you'd better turn to your tables. Those were grids of numbers and data to help you do your job. These were calculated by hand, of course, but were the central piece of information that organizations relied on. The problem was, they weren't always right. Imagine the errors you'd get if you calculate data based on numbers that were themselves wrong. It could result in a bad day. A young science aristocrat in London named Charles Babbage, while in college, had a look at the tables at the Royal Astronomical Society and was checking the math when he found numerous errors. Always the inventor, he developed a plan for a machine that would solve this problem, called the difference engine. The difference engine design had a lot of gears and cylinders and was operated by a hand crank, performing polynomial calculations with incredible accuracy. This machine was the first computer. It had a central processing unit. It had a way to reference its own memory to calculate, but it wasn't electrical, nor was it ever finished. You see, by the time Babbage began building his machine, manufacturing parts on his own, he got an idea of how to make the machine better. The new analytical engine was a streamlined and easier version of the difference engine and took 30 years to design and wasn't even built by the time Babbage died. A third machine was devised by Babbage during the design of the analytical machine, and this one was called the difference engine number 2. The machine operates on spiral columns and has a printing section, which was a really great improvement, but it too was never built. Several people have taken on the task of building these engines in their entirety, including Babbage's own son, who built segments of the analytical engine after his father died. The most recent build of Babbage's machine was when the Science Museum in London took his drawings and completed the machine after 17 years in 2008. It's a really great-looking machine, and it works just as Babbage planned. It's the year 1835. In New York City, a portrait artist works diligently in his studio. In the 10 or so years before, he had been commissioned to paint portraits and has since earned the reputation as one of the finest American portrait painters. During this period, he also founded a school tied to the National Academy of Design and had become one of the first fine arts instructors in America, teaching at NYU. This man, Samuel Morse, was working hard in his studio, not on portraits, but on a new electric experiment he had discussed earlier on a journey back from Europe. It was a discussion inspired by an experiment his professor at Yale years earlier had the students perform. The professor had 5 students hold hands. He shocked the first student with a static electricity charge, and the charge worked its way through all of the boys without stopping, demonstrating the transmission of electricity. Morse, also a lover of science, had remembered this when he had discussed the idea of sending electrical signals down a long wire using electromagnetic means, as others had failed and electromagnetism had just been perfected. Because Morse had been busy as a professor at NYU, had also been painting in his spare time, and was running as the mayor of New York in 1836, he had little time for this electromagnetic telegraph. However, his passion increased to complete his work, and he devoted his full time to the invention. In the process, he worked with a multitude of people on the business side, tooling side, and perfecting the operability of the device itself, creating the now famous system of dots and dashes called Morse code with his friend Alfred Vail. Congress came on board with the concept in 1844, allowing the installation of a telegraph line from Washington, D.C. to Baltimore, Maryland. The first telegraph, reading, "What hath God wrought," was sent on May 24th of that year. On the other side of the Atlantic Ocean in England, a piece of equipment that would prove to help the telegraph was created in 1846. It was called the printing telegraph and was an odd-looking piece of equipment. It kind of looks like a piano inside of a Singer sewing machine desk, but it was a first attempt at easily receiving and printing telegrams. It was a device that joined two 28-key piano keyboards by wires. Each key represented a letter, and extra keys served as a shift, which allowed some alternate characters for each key, like numbers or punctuation. One end of this system had a 56-character type wheel, which was kind of an early daisy wheel printer. The trick of this whole electromechanical system was the positioning. The two ends were calibrated to produce results at the same positions depending on what was entered at the sending side. As far as I can tell, the UK continued to use this device as late as the 1930s, according to a video I found on YouTube. I'll put the link in the description. In 1857, in Pekin, Illinois, a lawyer named Abraham Lincoln was spending time with a man named Charles Tinker, watching him use the new telegraph machine. Lincoln, always fascinated by technology, had gotten into a deep conversation with Tinker about the telegraph, how he converted messages into Morse code, and all the other details, including information about the batteries, the electrical coils that made the device work. In general, the whole thing took advantage of electromagnetism. Give me 30 seconds and I'll explain it to you. There are two ends connected through telegraph wire, those old phone poles with black cables along the roadside. One end was a key or a transmitter, and the other end was a sounder, or also known as a receiver. The key is the device that lays kind of flat and has a place for you to press your finger when you're ready to send a message, using Morse code, of course. When the key was pressed, it completed the circuit. And on the other end, the sounder pulled the circuit closed. The sounder had a pen attached to it with paper, and when it was pulled closed, it made a mark of either dashes or dots. Those dashes or dots on paper were the message, once it was decoded from Morse code. And that's generally how it worked. Mr. Lincoln, a technology buff and a very curious guy, was hooked. He loved it. When he became president a few years later, he became a big advocate for the telegraph, knowing how quickly it could get messages to his men in the field during the Civil War. And it was even known that he sat in the telegraph office for hours sending dispatches and waiting for responses. Telegraph lines quickly made their way across the United States and even across the ocean at the close of the century. One last person got involved with the evolution of this technology, French engineer Jean-Maurice Émile Baudot. Baudot came up with a system to make Morse code easier by taking the dots and dash pulses and grouping them into an alphabet consisting of a combination of 5 dots and dashes each. These dots and dashes turned into off or 0 or on or 1, respectively, and were punched into a strip of paper. Oh, my IT friends out there, do you recognize where I'm going with this? 1s and 0s? Anyway, the paper was wide enough for 5 columns for machine reading, with room for sprocket holes down the middle. By doing this, he was able to create a full Roman alphabet, punctuation signs, and machine function controls like shift. For example, if a line read 000-11, that was received by the machine as a letter A. The machine knew to print the letter A on the paper at the receiving end instead of the numbers. Though this transmission code was known as Baudot code, it was formally named the International Telegraph Alphabet Number 2, or ITA2, and eventually became a standard. I'm going to leave Baudot code here, but this isn't the last you'll be hearing of this data transmission code. I know I spent a lot of time on telegraphs, but it was important because this is the beginning of high-speed communication. These very telegraph lines later transmitted voice and then data, which became the World Wide Web. It's 1887. The Census Bureau had been hand-tallying the result of the 1800 census and was getting extremely concerned about how long the next census was going to take, especially with the new surge of immigrants they were seeing. In 1880, 6.6 million immigrants came to the United States, and that number was predicted to rise to 9 million by 1890. At that rate, the census tallying would never finish. Desperate for a solution, the Census Bureau made a call for anyone who had a way to do this quicker. Enter Herman Hollerith, a graduate of college at age 19 and an incredibly smart guy. He began to work at the Census Bureau and quickly realized that processing the census was extremely tedious. It made perfect sense to him when the census asked for ideas about how to do the tallying quicker. So he turned to the Jacquard loom and its use of punch cards to input patterns. What Hollerith did was make a machine that consisted of 3 parts: a template in front of the user on the desk, a panel in front of the desk with clock-like counters so you could see the number of specific attribute, and a box to the side with slots for the cards. The way the whole thing worked is that you looked at the census entry and punched it in the template in front of you. For example, a 20-year-old male who is not married living in Michigan would be stamped as 20, not married, Michigan. When you're done punching holes for those attributes from your template, you put the card in the reader, which was about the size of a card and had a lot of metal rods like nails. If there was a hole in the card, the rods would go through, completing the circuit and adding to the count on the wall in front of you. If you had the machine set to tally people with a certain attribute, when you put the card in the reader, a bell would ring when it was successfully read and the door to a particular slot would open. You place the card in the slot and you're done. At the end of this, you got to open the door to the box and you could see all of the cards sorted by age, state, etc. So that Michigan card would be in the Michigan box. The Census Bureau loved the idea and leased the Hollerith machines. The machine was so helpful for the census that it cut time for counting the 1890 census down to 3 years. It took 7 years for the 1880 census, and that with 9 million less people to count. The Bureau was ecstatic, and so was Hollerith. He had established a business called the Tabulating Machine Company. His company quickly grew and expanded into the railroad business. The New York Central Railroad leased Hollerith's machines after some adjusting to keep up with the speed of railroad operations. Hollerith also created new punch cards for general business needs and did things like add dollar signs to columns. Clever guy. The Tabulating Machine Company was wildly successful. They had the right to all the machines at the right time, and Hollerith continued to work hard at his business all the way up until his retirement in 1911. He ended up selling his business for $1 million. The business who bought the Tabulating Machine Company, led by Thomas Watson, had also bought 3 other smaller businesses and merged them all into one big business, and in 1924 renamed that company International Business Machines, or IBM. Well done, Mr. Hollerith. We've come so far. We can communicate quickly to anyone across the country. We've figured out how to count a lot quicker than we did in the past, and with way fewer mistakes. And we saw the birth of the first computer, though it took 130 years to actually build the whole thing. Regardless, things are happening and the future is looking bright and ready for a bunch of miscellaneous inventions that, though they don't mean anything at the time, will come in handy in the future. Next time, we look at a section I call Fun with Electricity. we see the invention of the vacuum tube, magnetic tape, drum memory, and we get in the middle of a battle between a farm boy and NBC. Thanks for tuning in. We'll see you on the next leg of the journey.